So covariance is the measures, right? It measures the direction of linear relationship. Measures the direction of linear relationship. So there can be three directions. Both are increasing together, okay, or one is increasing, one is decreasing. The third option is the x is changing but nothing is happening in y, zero correlation, independent. Okay, so okay, so there can be three types. Okay, the covariance can be one, positive, if x increases then y increases. Two, negative, if x increases then y decreases. And three, zero, x increases then y no change. These are the three possible options, that if one variable x is changing then y is changing or not. Say for example, simple, age of a person is x and height of a person is y. So as x increases, y increases. So there is a positive correlation. If as the age of some person, of a child increases, the height will increase. So there is a positive correlation between those two, right? So that's what it measures. Simple, a simple example. Okay. So let's see a simple example and understand. So the formula also I'll mention. So there's a sample. Say again, when we talk about this these metrics, there'll be a sample covariance and the population also, population covariance also. So the sample the population covariance is measured as population covariance. So that is for the complete population. For example, if I'm talking about population, means say for example if I'm saying that the average height of a city is 5 feet 7 inch, means I'm talking about the population, but I will not go and take the height of each and every person, right? I take a sample and based on the sample I do the estimation, and because of central limit theorem etc we can say that, and if this number of samples is very large, we can say that the sample is a very good estimation of the mean. As the increases, the sample mean will converge to the population mean. So we have population covariance first. Similarly, population covariance, it's given by sigma xy, x and y covariance, okay, is equal to sigma sign, similar to standard deviation x and y, but it has two variables x and y, equal to 1 to n, and then we have xi minus mu x, that is population mean of x, and yi minus mu y, population mean of y, by total number of samples. So this is what it gives. Okay, so distance of mean of the for the first variable and distance from mean of the second variable divided by the total number of the samples in the population. This is population. Similarly, there is a sample covariance, the sample that I have. This is given by s of xy. This is equal to sigma I equal to 1 to n. Similar, but just instead of population mean, the sample mean will come. Xi minus x bar is the sample mean, and yi minus y bar is the, and this will be divided by n, but this is a biased estimate and we divide by n minus 1, that is Bessel's correction. I have told you earlier too. I'll create another video for why this n minus 1 comes. There's a mathematical derivation plus some intuition also, that why we make this correction, so that this becomes unbiased. Just taking n is a biased estimate, and if we just take n minus 1, that will be an unbiased estimate. Okay, because of this is coming. This is an unbiased estimate. For now, just assume that, and this is called Bessel's correction. This is the formula. So, so we have a lot of samples. So distance between these, okay, if x is changing and the corresponding y, if this is plus, right? If both are changing in the same direction, okay. So if the change in delta x, xi minus x bar, so if delta x is positive and delta y is also positive, so both are changing, means if x is positive then this is also y. So the net, I will do a sample, right? I will do multiplication of all and take the summation against all, and the net, if it is positive, this is positive positive, or both are changing in the same direction. For example, if delta x is negative and delta y is also negative, so net sum of this, the product of these two would be positive, because that's the multiplication, is delta x. I'm just denoting this x minus x bar as delta x. Okay, just a symbol, and this y minus y bar is delta y. Simple. It's not that this is for the difference. So if it is positive, both are positive, then also this will be positive. Positively correlated means both are changing in the same direction. If this is negative, means then also they are positively correlated, means both are changing in the same direction. If one is decreasing, means other is also decreasing, means positively correlated. Changing in the same direction, it measures the direction of change. Okay, that's what I mentioned. Direction of linear relationship. Okay, so that's what it. And if it is the other way around, if one is positive, other is negative, one is positive here and other is negative, means they are changing in the opposite direction. One is increasing, other is decreasing, and the vice versa. Let's see a simple example and understand. For example, we'll do a sample covariance. For example, it's a very simple example. 1, 2, 3, and y is equal to double of it, 2, 4, 6. You can clearly see that x is equal to y is equal to 2x. There's a clear relationship. Okay, there's a clear relationship. Y is equal to 2x. Means they should be, the covariance should be positive. Okay, so let's compute it quickly and let's see. So covariance formula is, what is the formula? And here this will be the mean. This is the mean and this is the mean. So x bar is equal to 2 and y bar is equal to 4. And then sample xy covariance is equal to sigma summation of all x minus x bar. So x1, I'll take xi. So this will be 2 minus 1 into corresponding 4 minus 2 plus, that is a summation, then 2 minus 2 into 4 minus 4 plus 3 minus 2 into 6 minus 4 by number of samples. N is 3, but we'll do an unbiased estimate, so this will be 2, 3 minus 1. This is equal to 2. So this will be 2 minus 1 is 1, 1 into 2, this is equal to 2 plus 0 plus 3 minus 2 is 1 and 6 minus 4 is 2. So this will be equal to 2. So my sample covariance is 2. These are simply we calculate covariance. Very simple, no problem. And that's what it shows, that this is positive. Okay, the magnitude, okay, it just tells me it should be positive or negative. The magnitude doesn't matter here. So this means that positive correlation. And that's what we see here. That y is equal to 2x. If y increases, x increases, y will also increase. It's simple. One, it's just a double of this. I hope this is clear. Okay. So this is scale dependent. If the numbers would be high here, say for example, if I increase the number 10 times, 10, 20, 30, 20, 40, 60 like this. So this scale will, so this will become 20i, understand? So you can do the maths. If I change these numbers, the scale will increase. So this is dependent on scale. Okay. But for us, only the final value, whether it's positive, we just care about the direction, whether it's positive, greater than 0, equal to 0, or minus or negative, less than 0. Okay, positive, negative, we have said, right? Greater than 0, less than 0, or equal to 0. Only we get the direction. The magnitude is not important. Okay, and that's what. So if you want to compare two different data sets, say for example, I have one data set which gives me the covariance of my age and height. So I'll get some covariance as xy. And there's another, say for example, years of experience and salary. This will be another covariance, x dash, y dash. So the units of this will be different. So I cannot compare whether this covariance is high or this covariance, the relation, which is more, means the covariance, which gives more information about the mutual change of these two variables. So I cannot compare, it just gives me the direction. That's the drawback of this. So I'll write it. Drawback is covariance only measures direction. Covariance only measures direction, whether it is positive or negative, but not the strength. How strongly they vary together, but not the strength of variance. Okay, so that's the thing. So that's the drawback.